Hello, and welcome to the short 20-minute wrap-up of basically, I know it says chapter 5 here, but we're looking at chapters 2, 3, and 4, and basically we're looking at the chemistry that you should already know in order to kind of understand this class and to understand specifically chapter 5. And so we are going to go on. Okay. So again, I'm going to do a review on this, but I am assuming that you guys know all this material. There's plenty of materials on the web that you could go on, and your book is an excellent resource as well. Basically, what you should already know is that life is made up of a number of particular elements, and the vast majority of about 96.3% is made up of oxygen, carbon, hydrogen, and nitrogen, and these four make up the vast majority of the molecules that we'll be looking at. We have another set of not molecules, but atoms or elements: calcium, phosphorus, potassium, sulfur, sodium, chlorine, and magnesium, that make up the vast majority of the rest of it. And so again, these 4, 5, 6, 7, 8, 9, 10, 11 molecules make up the vast of what we've seen. Sorry, I shouldn't say molecules, these elements. Again, there's a number of elements that we call trace elements because they're needed in very small amounts, less than 0.01% of the mass. They are very critical, though. You will not survive very long without your iodine or your iron. We don't have large stores of these inside the body, but what they do, and they help proteins function, they do very well, and we will talk about that a little bit later. Now, you should understand the difference or the similarities between atomic number and the atomic mass. An element's atomic number is basically the number of the protons in its nucleus. Now, this isn't all that determines the chemistry of a cell, but I'm saying cell and molecule, and I don't mean that. What I'm meaning is an element, and it's atomic number, which basically tells us what that element is. Now, this element can have a mass number that's due to the addition of the number of protons as well as the number of neutrons that we see inside of there. And now again, an element, the same element, can have different numbers of neutrons inside of it, and it would change its mass, but it would not change its atomic number, and therefore not very much change its chemistry. And again, for life, we really don't have kind of odd elements in life anyways. And then, so again, the mass, the atomic mass is the atom's total mass. Again, a lot of the properties of an element is going to be due to the valence electrons, or that the electrons in the outer shell, which kind of determine the shape of the element. And I'm not going to get into that big. You should get into that in biology. Again, atoms with incomplete valence cells can share or transfer valence electrons with certain other atoms. Again, that's share or transfer. Sometimes it's better to give, if you have one extra, it's better to give up that one extra than to kind of hunt around for all the rest of these. And these are what we call chemical bonds. And it's the breaking or the making of these chemical bonds that really kind of gives us the chemistry that occurs in life. Now, in terms of bonds, there's relatively strong bonds, and one of them is what we call a covalent bond, which is formed when we share a pair of valence electrons, and that's electrons in the outermost valence shell. An example of this is, here's a hydrogen atom with an electron spinning around there. We call them an electron cloud, and then when these two come together, they would share those electrons. So there's 2 electrons in an outer valence cell of these guys, and they share those 2 electrons, and they go round and around. And so that would give us a structural formula, and then again we can use a molecular formula in which it is assumed that that bonding occurs. And so this is looking at one bond between each of these 2 hydrogens. Oxygen can share up to 2 sets of these valence electrons, and so we see a double bond there. Water would share an electron because this oxygen can share two oxygens in there. Oxygens and two hydrogens can share those electrons, and again, due to the electrons over here, again, this water has this kind of odd shape about it. And then we have a methane, which is actually a very symmetrical molecule on there. If we look at this, it has actually, there's a symmetry. And so in this one here, we're going to see a little bit of polarity, a little bit of a positive charge over on this side, and then we're going to see a slightly negative charge over here. Whereas this molecule in here, we don't see that because that sharing is equally, and it's spatially equally. Again, that would be an example of a nonpolar covalent bond. A polar covalent bond would be like the bond that we have in water, where those, again, electrons are not necessarily shared equally. And I do a thing where I stand up on top of a chair really to show this. And again, this is just showing you what I showed before, in that, again, when we look at this in total, there's no difference in charge here. The negative charge over here is negated by basically these two charges over here, and it's a vector quality. I'm not going to get into that. Next, we will talk about ions, charges that a molecule can have. A cation is where it has a positive charge, and anion is where it has a negative charge. An ionic bond is one where we have a full positive charge and a full negative charge, and those two will stick to one another, and it's a very, very strong bond. A hydrogen bond forms when hydrogen atom covalently bonded to one electronegative atom is attracted to another electronegative atom. In living cells, the electronegative partners are usually oxygen or nitrogen atoms, and we'll use this quite a bit. And here's a case where they come together, and so we're going to have a partial positive charge on this hydrogen over here with a partial negative charge on this nitrogen, and they will stick together. It's not a full, so that's why we have this little delta up here, the Greek delta. I believe it's a delta. No, it's not a delta, lowercase delta. So stick together, but you know, again, here we have this partial positive charge here, partial negative charge over here. On both of these, when we look at it, there is no charge, but in this little area, we will get a difference, and it is very sticky. Again, the properties of organic molecules depend on basically the carbon skeleton and what components are attached to it. I also call those kind of little moieties. Again, why I put this slide in here is to kind of look at a chemical reaction that we have. And so we have our reactants, and then our reactants come together to give us a product. And then again, this situation, although this doesn't happen here, can be an equilibrium where it goes backwards and forwards. This is photosynthesis. Again, if we look at this, if we add up the number of carbons, we have 6 carbons here, and lo and behold, we have 6 carbons here. So we don't have elements just kind of disappearing. It's very critical that you know how to balance these equations and try and do that. But again, when we go from carbon dioxide and water to sugar, C6H12O6, which is glucose, that is photosynthesis, and that's one of the more important chemical reactions that we can do. Another thing that we need to look at is this idea that we call a chemical equilibrium. And chemical reactions are reversible. That reaction that I showed you there is a reverse reaction. That's actually called respiration. Now, not all of them are exactly equilibrium, but we will talk about this when we talk about energetics, is that a lot of times when a reaction goes forward, that reaction could just as easily go in the opposite direction. And when the forward reaction is the same as the backward reaction, in which case nothing is happening, no net change is happening, no change, then this equation is in equilibrium. Okay. This here is showing you some of the properties of water. So here's a water molecule. A water molecule could hydrogen bond with another molecule over here. What's really kind of interesting is what's the temperature? How much heat do you need to put into a system in order to break a hydrogen bond? And I would say that's 100 degrees Celsius, and we'll talk about that a little bit. Again, the idea of heat is we're looking at a calorie, which is the amount of heat required to raise the temperature of 1 gram of water by 1 degree Celsius. So if you were to raise the temperature of 100 grams of water 1 degree Celsius, that would be 100 calories. Or if you were to raise the temperature of 1 gram of water 100 degrees Celsius to boiling, that would also require a 100 calories. And then, again, when we look at calories in our food package, the calories are a relatively small unit of heat, and so we need to use much larger, and so we use kilocalories, which is 1,000. Now, I do like using joules, but there are some important parts of using calories because everyone has it. But the joule is actually to look at a Newton of force, and we won't get into that here. What we call specific heat of a substance is the amount of heat that must be absorbed or lost for 1 gram of that substance to change its temperature by 1 degrees Celsius. The specific heat of water is basically 1 calorie per gram per degree Celsius. Water resists changes at temperatures because of its high specific heat. And so when we look at water, you have to put a lot of energy in there in order to change the temperature of the water and also to bring that water to the boiling. So ice floats in liquid water because the hydrogen bonds in ice are more ordered, making ice less dense than water. Water reaches its greatest density at 4 degrees Celsius. And so there's a number of temperatures, like body temperature of the human being, that you really need to know. And again, 4 degrees Celsius is an important one to know because water reaches its greatest density. And at 4 degrees, that water will sink. Again, ice does not sink. If it sank, basically all our bodies of water would freeze solid and they would never basically become unfrozen. And so this weird property of water, where basically the solid water is denser than the liquid water, allows our basically life to occur on our planet because, again, water does not totally freeze. Again, we need to look at water as, we call it the solvent of life, because basically the vast majority of our life is water. When we look at a solution, this is a liquid that is completely homogeneous mixture of substances. That means every square centimeter of that solution has exactly the same concentration in it. How does that happen? It gets really well mixed. And when we have a solution, the solvent is the thing that things are dissolving in. It tends to be the thing that you have the most of. A solute is the substance that is dissolved, and an aqueous solution is one in which water is the solvent. And so when we take a look at something like ethyl alcohol or a vodka or whatever like that, we're looking at something that is basically a 40% solution of ethyl alcohol in water. Water can also dissolve compounds made of non-ionic polar molecules. Even large polar molecules such as proteins can dissolve in water if they have ionic polar regions. And so in this graphic here, what we're showing here is this blue part is a protein, and that protein can have partial negative or positive charges, and this will get surrounded by water molecules, and if this molecule is small enough, this would go into solution. If the molecule gets too big, it would not be soluble in there. Again, we need to know concept of molecular mass, which is sum of all masses of all atoms in the molecule. And so if we have C6H12 and O6, which is a sugar molecule, we can add up the individual molecular masses of those elements to give us the mass of that particular molecule. Again, the number of molecules are usually measured in what we call moles. That's the number of molecules that we have in the molecular mass, and where 1 mole is equal to 6.02 times 10 to the 23rd molecules. So if we were to weigh hydrogen, 6.02 times 10 to the 23rd molecules, that would be 1 mole. And this is Avogadro's numbers, and in unit Dalton were defined as such as 6.02 times 10 to the 23rd Daltons equals 1 gram. So molarity is the number of moles of solute per liter in a solution. And what's really kind of interesting here, so this is a concept of pH. acidity or basicness. A pH of 7 is neutral pH. A pH above 7 is basic. A pH below 7 is acidic. And we're trying to get away from using hydrogen ions, which we kind of went in the past, and we would call this aqueous hydrogen. But basically what happens is water can disassociate by itself, and it does at a small level, and then what happens is one of these hydrogens is put onto a water molecule, and we get a hydronium ion, which has a positive charge, and we get a hydroxide ion, which has a negative charge. And again, this hydrogen can quickly either go back and recreate the water, or this hydrogen can be shared with other waters and move around in there. And basically this happens at some certain value that gives us the pH, and I'm not going to get into this too much, what the pH. We do need to have an idea of what an acid and a base is. An acid is any substance that increases the free hydrogen ion concentrations in a solution. A base is any substance that reduces the hydrogen ion concentrations in a solution. And this is an interesting concept, but just memorize this for now. Strong acids and bases dissociate completely in water. So what happens is strong acid, when you put it in water, all the hydrogens that it can give up, it's going to give up. Okay. Weak acids and bases are reversibly released and accept hydrogen ions, but can still shift the balance of the hydrogen and hydroxyls away from neutrality. And so this is also a concept of what we call a buffer, and we'll talk about that in a little bit. The internal pH of most living cells must remain relatively close to a pH of 7. Buffers are substances that can minimize changes in concentrations of hydrogen and hydroxyl ions in a solution. And so that is, at a certain pH it would accept hydrogens, at a certain pH it would release hydrogen ions. Most buffering solutions contain a weak acid and a corresponding base, which combine reversibly with the H ions. And so in this case here, carbon dioxide can cause acidification of the oceans because basically of this reaction right here. And this is calcium carbonate, which is used to make, of all things, these reefs down here. And what's happening is when the acidity of the ocean, so what's happening with the ocean is we would have carbonic acid being made. And so what happens in this carbonic acid is that this CO3, the calcium carbonate that's being made, is going to be released, and then it will bind with a hydrogen ion to give us the HCO3 negative. And so that's due to the presence of carbon dioxide in the atmosphere. And so as this water acidifies, the hydrogen ions combine with carbonate items to produce bicarbonate. Okay, carbonate is required for calcification, production of calcium carbonate by many marine organisms, including reef buildings. And so when we get this bicarbonate, that is taking actually carbonate from calcium carbonate. Again, we're learning a little bit more of this. The next thing that we need to look at is structural shape. And so structural isomers are molecules that have the same molecular formula, 1, 2, 3, 4, 5 carbons and 12 hydrogens. If we give them this shape, this is pentane and this is 2-methylbutane, these have the same molecular formula, but they have a different shape, and therefore they have different properties. We also have what are called cis-trans isomers, and that's where, again, on a double bond over here, which is a relatively flat bond, we can have two molecules being on the cis or the same side, or we can have two molecules, two moieties here being opposite sides, and this is what we call cis-trans isomers. We can also have enantiomers, which are basically the left, or yes, the left and the right hand. I'm holding up my left and the right hand. And that's the L isomer and the D isomer, or the R isomer, dextrose. Again, this is a difference here that we're looking at here. So this is cholesterol, and this is a big difference that we have testosterone, which I have a lot of, estradiol, which I have relatively lower amounts of, but women have a lot more of here. If we look at these molecules, they look very similar, and except for these additions here, okay? And so again, those little things can become a big difference. So what we're looking at is functional groups, or I also call these moieties. The functional groups are components of organic molecules that are most commonly involved in chemical reactions. The number and arrangements of functional groups give each molecule its unique properties. And so again, those molecules that we're looking at here, these molecules are vastly different. But if we look at their molecular structure, not so much. I need to go on this. So basically what we need to do is the 7 functional groups that are most important to life: the hydroxyl, carbonyl, carboxyl, amino, sulfhydryl, phosphate, and methyl groups. And so again, please take a look at these when you get a chance.